So this was the last thing that we discussed in the class, and we were about to start off with universal time, right? Okay. So are you able to see my screen?
No, sir. Now, okay, sir. Yes,
Fine,
yes.
fine. Okay. Thank you for that confirmation. Okay, so we will continue our discussion with regards to universal time. The previous thing, if you can just recall, we were discussing about the tropical years, right, and how to calculate and how to find out if it's a leap year, then how to put it in the format of Gregorian calendar. Then we even spoke about Julian calendar, the importance of calendars, and how they are divided with respect to Earth's motion, with respect to sun, right? So continuing our discussions with time, okay, there is another important thing to be kept in mind is the universal time. Universal time coordinated, in short, it's also called UTC. Okay, is the time used for all civil keeping purposes. So when I say civil keeping purposes, it means that we are using it we are using it for all normal regular purposes, day-to-day purposes. Okay, and it's the time reference which is broadcast by National Bureau of Standards, just like how we have few standards. Now, can some of you tell me uh, the name of few regulatory bodies that we have right now? Can you name a few regulatory bodies in India, or any regulatory body for that matter? Yes, there are n number of regulatory bodies, right? Kavya, can you name them? At least one. Kavya Shri, Kirtana, or any of you for that matter. Can you name a regulatory body? Okay, so Telecom Regulatory Authority of India, right? So that deals with all our telecommunications. Similarly, there is Bureau of Standards, okay, with respect to time. So they are with respect to the accuracy maintenance of time, because it has to be maintained throughout the same. It is based on an atomic uh, time frequency standard. Many of you would have heard of these atomic clocks, right? So they are very precise. The fundamental unit of UTC is mean solar day. Okay, just like how we have our day, which is divided into 24 hours and 60 minutes and 60 seconds. Similarly, the mean solar day is divided in the same fashion. Okay, so if we multiply, so we will get about 86,400 seconds in a day. Okay, so day you multiply into minutes, minutes again you multiply, so 24 into 60 into 60, so that gives us about 86,400. Satellite orbit epoch time is given in terms of UTC. So this epoch time, so we will see actually a problem based on epoch time, and you will come to know as to how much of calculations happens with the decimal part. Universal time is equivalent to Greenwich Mean Time, which is GMT. Okay, now you would have seen in your cell phones GMT plus 5.5 hours, right? So it refers to India. So similarly, every country will be having its own time zone. Okay, GMT minus 5.5, plus 5.5, minus 4.5. So based on where it is located, the time zone changes. Right. So this was the numerical that I was talking about, which is for the calculation of time in days, hours, minutes, and seconds. Okay, for an epoch day. Okay. So with 324, we are not bothered. We are only bothered with this 0.95. So it is almost 325 days. Right. So with this 0.5, we are going to calculate 0.95. Okay, 0.95. So that this is going to be multiplied with 24 hours. So I am converting this decimal into hours. So how do I do it? I can multiply with 24. So if I multiply with 24, it's almost 23 hours. Okay, because you can see here that it's about 22.94, right, which is almost 23 hours, but not 24. Right. Okay. Then again, I take the decimal part here, which is 0.9480022. Now that I know that it's about 22 hours, right? Then I take that fractional part, and then that's going to be my minutes, because this is hours and this is minutes, right? So this one I multiply with 60. Okay, and I get 56. Okay, so I get to know that it is 56 minutes, and it's 0.881344 seconds. So what I will do now, in order to convert this into seconds, again I will take this fractional part and then I will multiply with 60. Okay, and I will get about 52.88. So finally I combine everything. Okay, I combine this 22, and then I take this 56 minutes, and then I take 52.88 seconds. So this is happening on the 324th day. So because I have put it as 324.95616.765, so on the 324th day, okay, all these are going to happen. Fine. So how is this happening? We are considering actually the decimal part, and for hours we are multiplying with 24, for minutes we are multiplying with 60, and for seconds also we multiply by 60. So I take everything uh, such as 22 hours. So this is going to be my final epoch time. Okay, so the epoch is at 22 hours 56 minutes and 52.88 seconds. So this is like a dead time or conversion from one point to another point. So now, like how we keep sun as a reference, we can also keep the stars as a reference. Okay, and that is nothing but called your sidereal time. Okay, so not only you can keep time with respect to sun. Okay, you can also do it with respect to stars. So how do we do it with respect to stars? With respect to the fixed constellations. Okay, just like how we discussed in the previous class, there are a lot of constellations. So we can keep one constellation as reference, and to the point it comes back, it revolves. As we all know, the earth revolves, right, and rotates. So it should come back to the same point again. So that is referred to as sidereal time. Okay, so let's consider this information here, which is sidereal time is measured relative to the fixed stars. Okay, fixed stars. Now this is important. How stars are constant. Okay, except that some uh, during the death. Okay, they actually move from one point to another as the energy drains down. The sidereal day is defined as one complete rotation of Earth relative to fixed stars. Now, not with respect to Sun, this is happening with respect to stars. Okay. So here also we have 24 hours, 60 minutes, and 60 seconds. The only thing that we add here is sidereal. Okay, 24 sidereal hours. Okay, and one sidereal hour is equal to 60 sidereal minutes, and one sidereal minute is 60 sidereal seconds. So 24, 60, 60, the same formula is applied. Fine. Now, this is how. Okay, let me just zoom in a little so that it becomes comfortable for all of you. Okay. Now this is your sidereal day. Okay, one sidereal day. Why is this one sidereal day? Because we have fixed stars. Okay, and the Earth moving from one point to another point. And this is your solar day. What is solar day? Keeping sun as the reference. Okay, from the time it the sun rises to the sunset. Okay, so we take that as one reference. Okay, so this is how we actually calculate things. Okay, so now if we talk about numbers, okay, how much is it? So one mean solar day. Why do I call it one mean solar day? It's because we average things out. Okay, I just cannot take data with one information. So what I do is I average things. The more the data I have, the best average or the best mean I will have. Okay, so if I have the best mean, then that is going to give me the approximate information, which means the most accurate information, right? Okay, so one mean solar day is equal to about 1.0027 mean sidereal days. Okay, so this is equal to about 24 hours, and it's actually extra, 3 minutes and 56 seconds. Okay, so we had calculated about 84,000 seconds, right? So here it changes, it becomes 86,000 because of this minutes here, right? Because of this minutes here. Then one mean sidereal day, okay, sidereal day is equal to, okay, just the opposite, is equal to about 0.99 mean solar days. So which means a solar day is much higher than a sidereal day, which is very much evident with our diagram in the previous slide, right? So here you can see your solar day. Okay, your solar day is much higher, okay, or larger than your sidereal day. So with respect to stars it is less, with respect to sun it is more. Okay, okay, so let's move on to the next one. So you will have to kind of remember these, so that if a question is asked, then you can remember. The use of 23 hours 56 minutes as an approximation for mean sidereal day will be used later in determining the geostationary orbit. Now, geostationary orbit is very important. Why do I say that it's very important? It is because most of the satellites, or almost all of the satellites that we launch, we actually keep them or put them in geostationary orbit. Okay, so these solar days and sidereal days and the timings related to them are very important. Okay, because it will help us in determining or extracting information with regards to geostationary orbit. Okay, local mean solar time and sun synchronous orbits. So these are the two topics that we will be discussing right now. So major types of orbits for our Earth are inclined orbit or geostationary orbit. So as I told you, our Earth is actually inclined about 23 and a half degrees, right? Okay, so similarly, our geostationary orbit, okay, or sorry, here do not get confused. Inclined refers to synchronous and equatorial refers to stationary. Okay. The orbit directly above the equator is called equatorial orbit. Geostationary type of geosynchronous orbit has an angle 0 degree. Okay. Stationary does not have any inclination, but your inclined orbit has an angle of inclination. So polar orbit or sun synchronous orbit. So these are the terms which we will be looking into one by one. Now, a question if asked, what are the properties of geostationary orbits? So this is going to be your answer. Okay, and Varun has answered UGC, AICT. Yes, these are also the regulatory bodies. Fine, thank you. Now, with regards to geostationary orbits, it's directly over the equator and it's circular in shape, and the height is about 36,000 kilometers from the surface of the earth. Okay, from the surface of the earth, it is about 36,000 kilometers. So you should just move straight up. West to east movement same as earth. Okay, so just like how we have west to east, in the same way your geostationary orbit also has its movement. Speed is the same as Earth's rotation, so which means we are replicating those properties which we see here on Earth, okay, on the orbit. Okay, and similarly appears stationary from Earth. Okay. So this is very important. Okay. So if you see at any point from the Earth, your satellite will look constant. Okay. So that is because the speed is actually in sync. These are mainly used for communication purposes, and the drawback, it can't cover the polar orbits. So that's the only drawback, because the movement is from east to west, right, west to east. So from north to south, where we have these polar caps, only those can't be covered with geostationary orbits. Okay, apart from that, everything is the same. Okay, so just go through the points given here. Okay, so that's the only drawback with regards to your geostationary orbit. So it cannot cover the polar ice caps. Okay, fine. Now with regards to geosynchronous orbits, right, you can see these points here. Okay, wherein just like your stationary, okay, but these have inclined orbits. So that's the only thing here, where it has inclined orbits, and the period of revolution is approximately 1 day. Okay, so these satellites can take about 24 hours to move around the earth, just like how we have 24 hours. In the same way, uh, geosynchronous also does take the same time, and the velocity of these satellites is equal to angular velocity of the earth. Okay. Why angle? Because the orbit is already inclined, right? So I should actually take at the same angle and rotate. So that's why it's called angular velocity. These satellites looks oscillating, not stationary, because of the inclination. Okay, so there's a slight tilt in the orbit. So because of that, we feel that these satellites, when they are in motion, okay, they are actually wobbling. Okay, they are not stationary. Geostationary satellite is a special geosynchronous satellite. So which means geostationary is also a section of geosynchronous. Okay? But then the degree, okay, the degree is just 0. There is only one geostationary satellite, but many geosynchronous satellites can be possible. Okay, so which means you can have many geosynchronous satellites, but you can have only one geostationary satellite. Can someone answer me why? Why is it so? Yeah, why is it so? Prajwal, can you answer that question? Prajwal, we can have only one geostationary satellite. Why? Can you answer that? Sandhya, Sharath, any answers? Anybody wants to answer that question? Okay, that's because you will have just if you have placed a satellite, okay, which is actually facing India, so it will actually be there, right? So you cannot that satellite is enough to actually cover our country and the neighboring ones as well, right? So you don't have to put another satellite for doing the same job, right? So only one geostationary satellite is sufficient. But if in case you want, you can put more geosynchronous satellite, okay, because our satellite can cover more than a country, almost a continent. Okay, here also it is not capable of covering the polar orbits. Okay. Inclination. Now next, polar regions. Next, with regards to polar orbits. So the inclination is approximately about 90 degrees from the equator. Okay, so now you should imagine your equator and then exactly perpendicular to it. So that is your polar orbit. They cover polar regions from North Pole to South Pole. Why did we come up with this polar orbit? So that in the previous one, geosynchronous orbits, we were not able to cover the polar regions. But right now, we can cover with the help of polar orbits, right? Which actually covers from North Pole to South Pole. Okay, they take approximately 99 minutes to cover one orbit around the Earth. Okay, So approximately they will take 99 minutes to cover one orbit around the Earth. So I can say it's about less than 2 hours, right? Less than 2 hours. And these orbits every time pass a location on Earth at the same local time. So because they are also in motion, the Earth is also in motion. So which means at same time they will actually be at same point with reference to Earth. Okay, so that is what you can keep in mind for polar orbits. Next, sun synchronous satellites passes through poles and also keeps changing its trajectory through the Earth. So just have a look at these points. So this is the importance of your polar orbits, right? So you can actually have access to your North Pole and South Pole. Thereby, you can cover. Okay, you can cover the uh, ice caps as well. Okay. Now, with regards to sun synchronous orbits, okay, sun synchronous orbits. Now, let us look into this. So the sun is here, okay, and the earth is here, and the level of tilts, okay, the angles that it actually makes is what we will be discussing with regards to sun synchronous orbits. So here you will have something called phi, okay, and here also there will be phi, and these lines, okay, the nodes that you have from this point to this point is called line of nodes, okay. And with respect to sun, all these angular calculations are done, okay. So let us see exactly how it is being done. Fixed angle between earth and sun and orbital plane of sun synchronous orbit. Okay, so we will take a plane with respect to sun and an angle that gets created between the earth and the sun. So plane, earth, sun. So these three things are needed. So these satellites are used to track changes with time as they move to same place at same time. Okay. So why is it needed? So because there are a lot of applications with respect to military, with respect to weather, right? And how your ozone layer, your O3 layer is getting depleted, the oxygen levels are getting depleted. Then how does it impact the global temperature? So these are the applications of your sun synchronous orbits. Okay, so you can have a look here where this is your sun, okay, and this is your equator, okay, just like how I slice it into half, and the angle that gets created, okay, so with respect to the poles. Now let's talk about the geostationary orbit. So a satellite in geostationary orbit appears to be stationary with respect to the earth. Yes, that one we have seen, hence the name geostationary. uh, Three conditions are actually required, okay, in order to keep them in proper place, okay, there are three conditions. So what are those three conditions? Number one, the satellite must travel eastward at the same rotational speed as Earth. So how do we calculate this? So we can keep the constellations of stars into reference, and we can calculate how much time it's taking for our Earth to meet the same point of these constellations, right? So once we have this, we can actually find out as to how much time it has taken to reach that constellation, right? And the orbit must be circular in fashion. It should not be other forms. So circular fashion should be there. Okay. So that is when we can actually look into these uh, travel time and all those things. Then the inclination of orbit must be zero. Now this is important. It should be zero. It's a must. So then only it's called a stationary orbit. If not, it's called a synchronous orbit if it has an angle of inclination. Right. Okay. So a precise geostationary orbit cannot be attained because of disturbance force. Now, as you all know, there can be a lot of disturbances when when the satellite actually moves into the atmosphere with regards to the drag, right? So this is nothing but called your atmospheric drag. So because of this atmospheric drag, that the travel time taken for your satellite is also going to increase, and it's very much dependent on the other external factors as well. Okay, so in practice a precise geostationary orbit cannot be attained because of these external forces that I spoke about, right? And the effects of Earth's equatorial bulge, the gravitational force plays actually an important role. Now how does gravity come into picture? How much close it's to the sun and to the moon, right? So all these effects are also taken into consideration. So the field radiations from the sun. Okay, now because of this gravitation, what can happen is, this is the impact, this is the result. So there can be a possible inclination of about 0.85 degrees every year. Okay, so if this inclination keeps increasing, then what is going to happen? We cannot call it as stationary orbit. So that's the challenge. We have to um, we have to keep our satellite in place so that there is 0 degree, okay, 0 degree inclination. So if in case the inclination, the angle of inclination is not kept zero, then we can see those wobbling effects, right? Okay, the Earth's equatorial ellipticity, okay, because it's like an ellipse, right? It's not a perfect circle, right? Causes the satellite to drift eastward along the orbit. Okay, so along with the orbit, what is happening? The satellite drifts towards the east. In practice, the station keeping maneuvers have to be performed periodically to correct these shifts. So, as I told you, every satellite we can have control. Okay, we can shift it either to the left or to the right or to the top or at the bottom. Okay, so we will have this thrust boosters. Okay, which will actually accelerate the satellite in whichever direction that we want to. Suppose, say for example, we want to shift it towards the left side. Okay, then you can find that these thrust boosters will actually activate on the right side, and it will push the satellite towards the left, and consequently with the other directions as well, right? So what's going to happen here? We are keeping a track as to where the satellite is exactly, and we are checking it, okay, if it's exactly in the orbit or if it's going off track. So if it's going off track, it becomes very difficult for us to actually control them, right? So if we just leave the errors to keep increasing, then what's going to happen if we allow the errors to increase? Can someone unmute and respond? Yes, can someone tell me what happens if it goes off track? It's a simple question, right? Will we be able to control the satellite's motion if it's going off track? Not possible, right? So that is one disadvantage if we allow the errors to keep on increasing. Okay. So what is going to happen here? We should make sure that these satellites are in place. Okay, so that we can have control via the base station, right? Also, the Earth's equatorial ellipticity causes the satellite to drift. Yeah, so we have seen this. An important point to grasp is that geostationary orbit, because there is only one value of A that satisfies equation 2.3. Okay, so what is that equation? So we have seen this previously, right? 2.2, 2.3. Okay, so I will show that equation. I've kept it somewhere so what probably what I will do is I will bring it back here again. Okay, so for a time of about 23 hours 56 minutes and 4 seconds, right? Communications authorities throughout the world regard a geostationary orbit as a natural resource, right? So this is very important. Every country wants to have this geostationary orbit, so that they can launch their satellites in these orbits, and they can have a clear look from east to west. Okay, so just give me a moment. You can just check the uh, chat box, all of you, and you can attend to it. Okay, fine. So every country is actually looking for this as a resource. Okay, the geostationary orbit as a resource, and everyone wants access to it. Okay, so tomorrow, what, or in the next class, what we will do is we will look into something called antenna look angles. Okay, so here we will see in what direction, okay, we are going to have a look at the satellite and how much angle that it's going to make. Okay, so all this we will see in the upcoming classes, wherein we will even solve few problems, and we will see what is azimuth angle. Okay, how far it is from the center of the earth, and how do we calculate as to where the satellite is exactly. So earth station, look angles, all these are very important parameters, and we will be looking into all these uh, parameters in detail. Fine. So I think we will stop here, and probably we will continue, okay, with the antenna look angles in the upcoming classes. So any doubts you have so far? If any doubts, you can ask me. Students, any doubts? Any doubts so far? Okay. So we will end the meeting. Okay, Sharath, thank you for answering. We will end the meeting, and we will get back in the next class. Thank you.